Hello, I'm Francesco Poletti from the ORC at the University of Southampton, and today it's my privilege to report our progress on improving the performance of Hollowcore fibers. This is a collaboration between two outstanding teams in my group at the university and at Luminicity, our spin-off. I would like to acknowledge all of my co-workers, and in particular Hesham Saker, Tom Bradley, and Greg Yashin, who have equally contributed and led this work. Hollowcore fibers, as we know them today, can be traced back to this seminal paper, science paper from 1999, where researchers at the University of Bath reported the transmission of 35% of the laser beam over a 40 millimeter long fiber. This, at that time, was a groundbreaking result. Now, since then, the technology has made enormous progress, thanks to contribution from various academics and industrial groups around the world, to the point that we are now talking about transmission through 4,000 kilometers, an improvement of 1 billion times. And even more importantly, the technology is beginning to make it to the commercial world. Last year, OFS has reported being able to cable this technology, these Hollowcore fibers based on photonic bandgap structures, to be used in 1 to a few kilometer data transmission links. More recently this year, Luminicity reported installing, in collaboration with EU networks, a cable in London using a different type of Hollowcore fibers, which is suitable for transmission up to tens of kilometers. Last week, British Telecoms reported tests and trials on this optical cable full of air from Luminicity, aimed at optimizing 5G networks and quantum key distribution. And at this conference, there has been a lot of discussion about Hollowcore fibers. It's been discussed at workshops on the first day, contributed papers. There is going to be a dedicated session just after this. We've had 2 invited papers, as well as 2 post-deadline papers. So beside this one, which is focused on the loss, my colleague Pierluigi Poggiolini will present in the slot just after this, but in a parallel session, our work on transmission of up to 4,000 kilometers of a full WDM signal. So what motivates all of this interest in Hollowcore fibers? Well, this is our closest solutions to waveguiding light in air. So if you can remove the glass from the core, immediately the nonlinearity becomes practically negligible. We have 30% improvement in latency, which becomes 20 times less sensitive to temperature variation. The dispersion becomes very low, backscattering 40 dB less than standard fibers. The polarization purity we can achieve is, again, orders of magnitude better than conventional fibers, much higher damage threshold, wide bandwidth, and low loss, which is the topic of this work. So these are some of the most groundbreaking fibers developed over the years that have helped the community improving understanding the physics and getting to where we are today, where arguably the most promising technology for this community is what we call nested anti-resonant nodeless fiber, or NANF. This has the lowest loss, widest bandwidth, longest data transmission distance in any Hollowcore fibers, as well as dimensions that make it compatible with splicing and cabling. When designing such a fiber, which is made of an arrangement of nested tubes, one important design parameter is the size of the inner nested tube. One can choose to work in a region where this tube is roughly half the size of the outer tube, like in this fiber. In this case, one can minimize the loss of the fundamental mode, but at the same time, also the loss of the LP11 mode, which is the lowest loss between all the high order modes, is at its lowest. So this is good for lowest fundamental mode loss, but it can lead to high intermodal interference, which is detrimental for very long reach transmission. Alternatively, one could choose to work in this other regime, where the inner tube is smaller. This has the advantage of increasing the high order mode loss. In this case, we increased by a factor of 30, which made it possible to transmit data through 700 kilometers in this fiber. The price to pay, however, is that the fundamental mode loss goes up a bit. So in this work, we we asked ourselves, how can we improve loss and intermodal interference simultaneously? For the same core size, the first thing one might want to do is increase the separation to the solid outer jacket. This reduces loss for all air-guided modes. Simultaneously, one might want to increase this cavity size that I indicated with Z, because this improves outcoupling of high-order modes to lossy modes guided in this cavity. Now, it turns out you can do both of these things by fabricating fibers that, rather than having 6 nested tubes, have only 5. And this is also shown by this simulation for ideal fibers. But you can see that going to 5-tube technology can allow you to reduce the loss of the fundamental mode and increase the loss of the high-order mode. Now, this is not a new concept. These groups have previously fabricated another 5-tube NANF and extensively simulated the performance of this fiber. What we've done here is exploiting our fluid dynamics expertise and engineering capability to fabricate optimized fibers. And this is an example of a fabricated fiber. Over the year, we've fabricated many tens of fiber kilometers at the university, a lot more at Unicity. It's a very well-engineered fabrication process. We typically yield from a few up to 6 kilometers per band, where the structural variation that we see are typically between 1 and 3% across the cross-section, for example, from tube to tube, but also between one end of the fiber and the other end. And these are the typical range of geometrical properties that we have targeted. So let me give you an example of the performance of one of such fiber. This fiber shown here has a core diameter of 34 micron and a thickness of around 400 nanometers. This is a transmission through nearly 2.2 kilometers of fiber, which we cut back to 500 meters. In both cases, we acquired 3 independent measurements with 3 different output cleaves to reduce measurement errors. And this is the measured cutback loss. As you can see in the zoomed-in version here, the loss in the C band is between 0.3 and 0.4 dB per kilometer, but it lowers down to the point that just outside the L band, between 1625 and 1650 nanometers, it reaches 0.22 dB per kilometer, which is the lowest reported loss in a Hollowcore fiber. We've also studied the modality of this fiber. We've done cutback using self-interferometric S-square method. And you can see here, this is where the position of the LP11 mode is supposed to be. And you can see that down to 25 meters of fiber, no peak was visible above the background noise. Only at around 15 to 10 meters that we could see the LP11 mode. Now, continuing the cutback with shorter and shorter lengths, we achieved very nice linear fit to a loss of the LP11 mode of around 2.8 dB per meter. Now, this is a very considerable improvement. So this fiber has a fundamental mode loss of 0.22 dB per kilometer, and for the LP11 mode, 2,800 dB per kilometer, both of which are better than the previous 6 NANF fiber we reported last year. So this is one fiber. We've also fabricated many more. I'm reporting here 3 more. If you're interested in the geometrical dimensions, you can read them in the paper. But what I want to show here is that the cross-section becomes progressively smaller because we are targeting operation at shorter and shorter wavelengths. How do they perform? Well, you've already seen the loss of this fiber. We've made this other fiber by thinning the membranes by about 50 to 70 nanometer. This shifts the transmission band so that it now covers the 1300 O band region, where it guides with a loss of about 0.4 dB per kilometer. Simultaneously, the loss is also 0.6 dB per kilometer at 1550. And this spike in the loss is due to water vapor in the fiber, which we have not paid particular attention to remove. But if you were to put dry gas inside the fiber, it would open up a flat region all the way. Now, to go to even shorter wavelengths, thinning the membranes further was complicated. So we decided to make actually the membranes slightly thicker and center the second operational window where we wanted. And we fabricated these two fibers, one centered at a laser delivery frequency of 1060 nanometer, where it reaches a loss of 0.3 dB per kilometer. These other centered where VCSELs and titanium sapphire lasers operate, around 850 nanometers, where it reaches losses of around 0.6 dB per kilometer, both of which through a very flat band of around 50 nanometers, 50, 60 nanometers, which is 8 to 10 terahertz. Now, this is how these fibers compare to state-of-the-art solid fiber. So here you can see pure silica core fibers and a more typical germanium doped core SMF. Now, as you can see, NANF-A and NANF-B have losses which are beginning to be very comparable to SMF outside the L band and in the O band. Clearly, some more work is needed to produce low loss also in the C band, but this is already very promising. Whereas at shorter wavelengths, these two fibers have a loss which is over a factor of 2 better than what is fundamentally achievable in conventional fiber. And this is the first time that Hollowcore technology have beaten silica at wavelengths of very significant commercial interest. Now, if you add this to the fact that the fibers are single-moded with virtually no linearity and with a dispersion that is between 2 and 4 picoseconds per nanometer per kilometer and very flat, you understand why there's beginning to be industrial interest in this technology. And as a further evidence of this, now fresh off the press, some of you might have seen this press release between Luminicity and Siena, where Luminicity took some of these 5 nested tube NANFs and put them in their cables. They made available two 2-kilometer cables with multiple strands in it, which were back-to-back connected to make a 20-kilometer total span of cabled Hollowcore fiber available to Siena. And Siena tested it first as a single span, where they found pretty negligible ESNR penalty, both at 400G using ZR optics and at 800G, and with plenty of ESNR margin, which encouraged them to put the same length of fiber in a recirculating loop, where they found over 160 kilometers at 800G and up to 2000 kilometers possible at 400G, which would be a millisecond scale latency saving over conventional fibers. This brings me to my conclusions. So we have shown that five nested tube Hollowcore fibers can achieve record combination of loss and high order mode extinction. We've reported 4 fiber with the lowest loss ever reported in Hollowcore fiber, and in particular 2 of them with the lowest loss for any optical fiber. We believe there is plenty of margin for improvement. We are already working on the next generation, and we think this is an excellent time for industry to get involved, test the technology, steer direction of travel, and accelerate the rate of progress. And if any of you is as excited as we are about this technology, bear in mind that we are recruiting. Thank you very much for your attention.